Hi, I'm Tom Stephenson, and welcome for Lecture 4B, and we're going to be continuing on with wall framing. You can find this material in Chapter 8 of the Understanding Construction Drawings for Housing and Small Buildings, and there will be some references to Chapter 10 of the CMHC Wood Frame Construction book. So Understanding Construction and the CMHC Canadian Wood Frame Housing Construction book, Wood Frame Construction. All right, so some of the things that we're going to try to look at is some of understanding how some measurements differ from drawings and actual framing requirements, the building requirements, the constructability, and identifying, distinguishing what exactly is optimum value engineering and why do we do it, maybe, and or why should we do it, and we still don't do it as much as we should. We'll also be looking at a number of areas of wall framing and stud size, orientation, and spacing. So some of the different methodologies, as you're aware, we space studs at a certain spacing. And like I said before, they may be 12 inches on center, they may be 16 inches on center, they may be 19.2, or they may be 24 inches. And it depends on how many floors it's supporting. It depends on the height of the walls as well, as you'll see. There's actually this table in the building code that gives you an idea of what you're looking at. And so this is for the type of wall. Is it an interior wall or is it an exterior wall? You got to remember, an exterior wall is going to be carrying some pretty heavy loads, with the snow loads going to be directly transferring through it from up above. So you could have a load-bearing wall that's an interior wall and a load-bearing wall that's an exterior wall. The exterior wall is typically going to be carrying more loads because the snow loads operating from around the roof transferring through the outside walls, especially if the house has roof trusses, because the interior walls are non-load bearing typically in a roof trussed roof. And we'll talk about that in the next lecture, or chapter 9 of the book if you read ahead. So this is just looking, non-load bearing walls, sizing for them. Maximum stud spacing, and just remember 400 millimeters is 16 inches, or 600 millimeters is 24 inches on center. Maximum unsupported height. So when they say maximum unsupported height, they're talking about how far it's going from plate to plate. All right. So from plate to plate, unsupported height between the members. And so if we're looking at the interior here, attic not accessible by a stairway. So that would be probably like for a story and a half, but it's not got an extra story up and above. It's just got kind of a storage area. And it goes step by step from attic not accessible by a staircase to attic accessible by a staircase plus 2 floors roof load. So it depends what it is actually supporting and how many floors that it is actually supporting. So these are giving you the size and spacing of the various members, and you can see in some cases you have to have 2 by 6s, and the spacing of the studs and the unsupported height. So how high it can go using that spacing and that sizing. So we usually will use 2 by 6s. We don't have to use 2 by 6s on an exterior wall. Usually what we're trying to do, usually the limiting factor on the size of studs on exterior walls very often is how much insulation can we fit in it. Are we putting styrofoam on the outside of the wall and then inside between the actual stud spacing, and what's the R value that meets, and does that meet the building code requirements? That's one reason. The other is, what is the unsupported height and how many floors is it supporting, and that will help to determine what's acceptable for the spacing. So we may not be able to use 19.2 on an exterior wall depending on what it's supporting up above. We may have to go with 16 inches on center instead. So those are some of the design requirements and considerations that fall into studs and stud spacings. Just like when we talked about floor joists, it depends on the span. And if we're going a really far span, we might have to go with a 12-inch spacing. Or if we're going with a ceramic tile to reduce deflection, we might want to go with a 12-inch spacing instead of a 16-inch spacing. So whether we do it with this or we clad with styrofoam, or now we tend to like to do 2x6s and clad it with styrofoam, or polyurethane foam between the studs, and there's different ratings for different insulations. So do we meet the current effective R values for the wall requirements? So optimum value engineering is kind of looking at, well, how do I reduce the actual surface area of the wood on the walls? Well, you could do that several ways. You could go with a 2-stud corner and use clips. So you remember we talked about in the previous lecture screwing the drywall on an inside corner with a 3-stud corner. Well, there's framing clips that you could use that would catch the actual drywall, and you could screw to that, and then you don't have that extra stud there. And the extra stud, which goes to the outside wall, it acts as a thermal bridge, so you lose heat through it. If you take a thermal imaging camera, and you can even Google that and check thermal imaging wall studs winter time, and you'll see a bunch of pictures that will show how when you take a picture from the outside, you can see where every stud is because it's losing heat through the wall. Whereas where the insulation is, it's not showing up bright orange or red because it's not losing that much heat. So we try to, with optimum value engineering, we're taking a sustainability perspective and trying to use less lumber and provide a more energy efficient building. It's one of those situations where if you use optimum value engineering, you use less lumber, so you can save on the extra lumber used and the installation of that lumber, and you get a more energy efficient building, and it still meets the structural requirements that you're after. You have to watch the building code as far as stud spacing because there's limits depending on how many floors that you're supporting above, but it can be a very sort of proactive way of saving on lumber and actually increasing the energy efficiency of the building, which is a win-win, right? Now you could really reduce the lumber by going with a single top plate, go at 19.2 millimeters on center, say it was a bungalow, 19.2 on center, and 2-stud corners, use 2x6s, so that could be a real energy efficient boost. But the problem is you got to make sure that your plates, then whatever is sitting on top, so say it's the roof trusses, they would have to line up perfectly with the studs. So now you got this concern of lining up the trusses exactly with the studs, which can often be difficult. What if you're going at 19.2, your studs are at your 19.2 and your roof trusses are at 24 inches? They're not going to line up, so you'd have to put your roof trusses at 19.2 inches. So you find that it doesn't get picked up as much. They go with the 2-stud corners, or they'll go with the 19.2 spacing, but not everything. A single top plate I have not really seen used for that simple reason. It's hard to get everything to line up in the design process. So it is a good idea to think about, and it's a good principle to understand, and keep that in mind when you're framing and you're putting together walls, that wood acts as a thermal bridge, not a thermal break, and try to minimize that during the construction process, but at the same time keep within all the code requirements that are there. So that can always be a little bit challenging, the single or double top plate ideology, because if you put a single top plate, you also have to put metal brackets across the top so it ties the two walls together wherever they intersect. Typically in regular construction, we just run the second plate overlapping the other, and then we nail it together, and that ties the walls really well. They're not going to separate. So this is what you end up having to do when you use that sort of optimum value engineering practice. And these would be the clips you would put in so that you could fasten the drywall to. I've not really seen that used all that frequently, but I think that's an easy one to do. So I'm not quite sure why it's not, but it is a pretty easy thing to put in, and it's pretty easy to screw the drywall to too, and it's very inexpensive to do. So that would be one definite move that I would be looking at. So currently not widely adopted, but I suspect you're going to see more of it if we don't see a totally different system come out, which is always possible too. That might be more effective and better than what we're thinking about and what we do currently. Sometimes we get stuck in this, we do this way, and then we just keep doing this way. We incrementally improve things. Optimum value engineering would be a way of incrementally improving it. Or somebody uses a disruptive technology that changes the way we do things, like ICFs instead of wood frame, but there seems to be a cost implication to that, even though it's probably a better system overall. So as long as there's that cost implication and we have an abundance of lumber, it is a renewable material. It doesn't require the embodied energy that concrete requires. It takes a lot of energy to make concrete. So environmentally, I would suggest that the lumber side would be a lot more environmentally sustainably productive than concrete, let's say. But we'll see. We'll see. There's lots of things out there. So when we do built-up wood beams and the transference, we talked about built-up wood beams. Remember, this would be called how many? What? 4-ply. So that would be a 4-ply beam. Well, we're never going to have less plies of the solid bearing underneath it. So we shouldn't have two studs carrying a 4-ply beam. So it's going to be at least that much. In some cases, you may have to put more than what the beam is, depending what it's carrying. Here we've got solid bearing underneath a girder truss. So a girder truss is a roof truss that carries the weight of other trusses. So these jack trusses run into this girder truss, and the weight from this section of the roof comes over to here, transfers down through that truss, down through that wall, and you want to make sure that that load, because it's so heavy, you don't want to just have it coming where those double plates are, because that would sag there. So when we got something like a beam or a truss, we have to put solid bearing underneath it. When we just have studs and a joist, we don't have to have solid bearing under it. But when we have a beam and we have it transferring loads down, we got to make sure this isn't going to sag, because that'll sag, cause cracks, it could even cause a failure if it's enough weight, like this could be. So we want to make sure those loads transfer. Not only do they transfer from the second floor down to the floor, then even on the floor below they transfer. So it transfers right through the building. When we're constructing the walls, we install temporary bracing that holds the wall straight as an arrow. So you have somebody with a line and they're adjusting it and they get the wall nice and plumb and straight. And that stays in place till you get the floor above and you get the subfloor on it. Then you can take the bracing off, because now it's not going to go anywhere. So it's sort of an evolving process. Temporary bracing holds things straight till you've got enough strength in the structure that it can stay straight on its own. So we'll take a couple of little close-ups of the Doncaster drawings from your textbook here. So this is where we've got a 4-ply beam coming across, and then the load transfers below. There's a point load above here, which means there's a post that's coming down that's supporting a lintel over top. So it's actually some jack studs that are supporting a lintel over a doorway, and it kind of comes down in the middle of nowhere over this floor. Well, you wouldn't want that column just coming down on the subfloor, because that would sag. So we put a beam in the actual floor, a built-up wood beam, and that's acting as a point, that's acting as protection or transference of that load to the actual built-up wood beam. And some of that weight's going to come back here to this steel beam, which goes across here, and some of that weight's going to transfer to the foundation wall. By judging by the hatching, this is a concrete foundation wall. So you can see that going on. We can see double joists around this window here, and this window here is fairly low to the ground, but there's no window well. In your book, you'll see the Brook drawings. They have a window well. This has no window well. So because it's so close to the ground, it's just up about 8 inches from the ground, you want to get some light in the basement. And so to get some extra space, because the first floor is very low to the ground, they've doubled this section with double joists up around in this area so that light can come through. So here's a close-up of the first floor that's right above that. So here's that lintel that I was telling you about. And if you look closely, it says L5. So you remember that chart we looked at in the previous lecture, and it said lintels, and it said L1, L2, L3, L4. Well, if you look at L5, it'll tell you the actual size of the lintel. And so that's either going to be, I forget what this one is, L5. I'd have to look at the chart myself, but it's probably 2x10s or 2x12s, judging by the opening. And so then that's going to sit on some jacks here. And that solid bearing is then going to transfer down to the floor. And that's right at that point, so that that weight then is transferred to the beam from that opening. So that's what I was discussing. You're always trying to think, how is the load transferring itself through the structure, right? And it's going from things like the roof, and the snow is transferring to the roof, and then that's transferring to the exterior walls, the load-bearing walls, through the trusses. And the trusses, if it's a girder truss, it's transferring that to the solid bearing, and that load's then going through the structure. It's being picked up by the next floor, going again through solid bearing, being picked up by the foundation wall, going through the foundation wall, hitting the footings, and transferring from the footings into the undisturbed soil. So we just kind of recapped the last few lectures with that little discussion. Here we've got a wide flange I-beam, and that wide flange I-beam is supported on a steel column, and the steel column will go to a column footing, which will pick up that load. And we talked about the supported lengths on each side, right? That goes in on it. Here we've got the kitchen area in the Doncaster drawing. So this is where the kitchen is going. They've got bulkheads that are for the upper cabinets. Bulkheads are one of those things, every 5 years they're in. Everybody wants bulkheads. Another 5 years goes by, nobody wants bulkheads. Another 5 years goes by, everybody wants bulkheads. So I don't know where it's at right now, but it's in or it's out. It's like wallpaper. Nobody wants wallpaper right now. 5 years from now, everybody's going to want wallpaper. It's just the way it is. So it's got no structural thing. It's just, it can hide stuff. It's really good at hiding pipes. It's really good at hiding ducts. It's a good way of concealing things, but it's also a good way to have cabinets come up to it when it's in style. All right. What's kind of big now is to have cabinets at different heights that go up and down. That's kind of popular. Okay. So you can see the metal bracing in place here. So you can see that. You see two double studs here. I think when they were doing it, they missed the solid bearing from up above, and they doubled this instead of put it exactly where it should go. And I think the building inspector made them come back and put double solid bearing here, because I believe in this particular case, this double stud goes right down to the floor below. And that is, if I recall, right here. You also notice the spray paint in here. This is the site super putting notes to the different trades on the wall. Not a bad idea. In case the trade goes in and starts doing something, they put notes to make sure you do this, make sure you do this, and mark things out so that they don't do something they shouldn't do. So just an effective way of communicating. It's all going to be hidden later anyway, so if it prevents somebody from doing something they shouldn't, then that's a good thing. You can see where the exhaust is going out for the fan. I think they have to move it. I think they put it in the wrong spot. You have to be very careful with all the measurements. If it's in the wrong spot, then maybe the cabinet is in the way. Maybe one of the gables for the cabinet, part of the cabinet is in the way, and then it's got to be moved. Much easier to move it at this stage, or better yet, put it in the right spot to begin with. You can see some of the rough-ins for the plumbing. You can see the drain. You can see the vent system here. You can see the water supply lines. You can see the outlet for the stove being put in, and the outlet for the plugs. And these have to be at the right height above the counter, where the counter is going to go. So these are all things that have to go in place. And if you're wondering what does this look like, or you can't imagine it, look at the Doncaster drawing floor plan, like we were just there. So that's this over here, and where the picture was taken over here somewhere, looking this way. That's that window that you see over here. This is where the sink is, so that's why the plumbing pipe is roughed in. This little symbol here is for a stove plug, which is a 220 volt plug, because stoves take a lot of energy. And there's a hood fan over top, which is going to require an exhaust. This is that solid bearing that I was talking about, SB, which is coming down, which is supporting the roof truss from up above. This is for a hose bib for your hose. This is the lintel sizes that we were talking about, L1. L7. L1 would be for the wood lintel. That's part of the wood frame structure. L7 would be for the steel lintel for the brickwork. This is a hatching indicating brickwork. This is a hatching indicating insulation, bad insulation inside a wall. So just giving you a little bit up on the drawing aspect, because it's hard to separate the two when you're teaching a course like this. So it's good for that to come together and get some understanding of what the drawings is saying and what we have to perform at. These drawings are in metric, so that's telling you 400 on center spacing. It's 300 on center spacing here. Well, depending on what you're doing and what's placed above, will change the spacing requirements for the joists. And so the joists are always above on the floor that you're standing on. So these sizes are for the second floor joist. When you're on the first floor, you see the second floor joist. When you're in the basement, you see the first floor joist. When you're in the second floor, you see the roof trusses or the ceiling joists. So if you ever forget, just start in the basement and say, okay, well, that's got to be the first floor. All right, so if I'm in the first floor, that's got to be the second floor. We've already kind of looked at this. This is where that solid bearing goes. You can also see that the joists are doubled here. And I think I mentioned that in the last, in lecture 3A or 3B. That was because they're a little bit longer spans. So to keep with 2x8s, they doubled them. That wouldn't be part of part 9. They would have had that engineered under part 3, because they don't have like doubling up of joists and stuff like that in part 9. So it would have been drawn by an engineer and they would have had their stamp on the drawings. This here is the lowering of the landing where you enter from the garage. You can even see the back of the stairs that's going to go up to the first floor. So it's a couple of risers from the sunken landing. Of course, that means you got lower headroom in the floor space underneath in the basement. This is how it's framed, and that's that lower floor space. So this would be the floor for the sunken landing where the laundry area is, and this is the floor where the kitchen is right above in the Doncaster house. So you're kind of over in this space here where it's framed out, and then you have the first floor up a couple of risers, and then there's the stairs going down to the basement. And this here is that cantilevered box window that we looked at in 3A and 3B. These are grade beams that are put in place, and that's to help stop the sagging of the concrete pad, because this is put in on fill, and the slab for the garage slab is put over that. So this is all going to be filled in with earth and compacted before this is poured, and then this gets poured with the garage floor later on. This is a better shot. You can kind of see it here, the sunken laundry area and that framing. So if you go back to these shots over here, this is what we're looking at. So if you're wondering what that looks like, this is actually this spot in here. It's a pretty good, reasonable rendition of the model. Yeah. And we can see here the double joist, the double joist, the double joist go around. We can see here, this is a load-bearing wall that's placed underneath a strip footing that goes around there. That dashed line represents a footing that this wall will rest on, which is this wall right here, underneath here. Good to visualize when you look at a drawing what you think this is going to look like. And the more you do it, and with the more experience you get, the easier it comes. And then you're going to look at things and you're going to see, well, something's missing or something's not right. And you might have to draw it out yourself and sketch it and try and figure it out. Or you might have to try it practically in situ to see what you can do with it, right? This is for that raised window that I was talking about. So where the double joists are around on the floor plan, this is the detail. So this is actually 6 inches above ground. And this is when it's brickwork, that's the 6 inches it has to be. We looked at the detail earlier on regarding that. And so what they do is they put a stiffener here. They put double joists around it so you get light that can come in through here. It's still a tiny window, so it's not great light, but it's a way of around keeping the first floor fairly close to the ground. A lot of people don't like to step up that much. It also makes it easier to make a transition from a sunken laundry area into a garage. So it's a very popular kind of design. There's this choice, or you could have a much deeper window and then put a window well. A lot of builders don't like to put window wells because they tend to be more warranty problems with them. So this is what that looks like. So when you're seeing something like this, you should be thinking something like this. So that's the stiffener, that's the double joists, that's the double trimmers, and these are the tail joists. And just going back here, so just that's your double joists showing around this window opening here, right? Notice where the lintel is over top of this. So what that looks like is this. The load has to transfer from the floor up above because you don't want this weight coming down over this weakened member. You want that load to be taken up by the lintel, which is going to spread that weight off to the sides and around where the window is. That's why that's marked where the window is. So you have a number of those components. This is another good detail, just looking at it, getting used to the components and what it means and what it says. We know what a lead-in brace is now and a cut-in brace with the metal bracing in. We know what temporary bracing is. I talked about the lapping over the plates when we use double top plates, which is practically all the time. And that's how that actually gets framed up there. Nobody frames like this though. We use a 3-stud corner. Not a good idea. Can you think why that might not be a good idea? Well, the biggest reason it's not a good idea is very often we put the sheathing on the wall, we lift the wall up, and then if we put them together, nobody's going to put the insulation in afterwards. And if you ask a framer to put the insulation in, good luck. Your best bet is you hire a separate subcontractor that does the insulating. Some framers are paid typically by the square foot. They want to get in, they want to get out. And if you don't see it, it's hard to tell whether it was put in or not. It ends up being a cold spot in the wall. You lose energy through it. So with those kind of things, systems thinking says, look at it, and is there a way that we can do it that people aren't going to mess it up? The work of Edwards Demings looked at when you have problems, consistent problems, common variation in a design or a process. It's typically not the worker's fault. It's typically the fault of the system. So can I change the system so I don't have these problems? Well, a 2-stud corner makes that better. A single stud, 3-stud makes that better. A 2-stud corner makes it even better because you don't have the thermal bridging. So you alleviate the problems. It's just the way of thinking about things that you develop over time, and it's sort of it's a way that if you start it early, it becomes a habit and a routine and a ritual, as I like to say. Here's another interesting sort of detail here, because there's a lot of stuff going on, and if we have to build this, we have to think about the constructability quite a lot. So you have an I-beam that comes across, and it's in a beam pocket. You also have a little bit of an extension here. And so what's going to happen, there's a lot going on in this foundation. You got a little solid circle there. You got a steel pipe column that's coming down that's supporting a bunch of things. And on the floor above, there's the steel pipe column. It's supporting this W200 by 27 by 180 by 10 PL. So it's a wide flange I-beam that's 200 millimeters high. It weighs 27 kilograms per meter. It has a steel plate welded underneath it to the bottom that's 10 millimeters thick by 280 millimeters wide. And that steel plate is going to carry the brick over the second floor. But in the room, there's going to be nothing. You won't know it's even there. It's going to be just a smooth ceiling. So what does that look like? Well, in the basement, that right here is this right there. So you're standing over here looking this way, and you can see how that little corner is out. It's not a straight corner. It sticks out just like here. It sticks out 100 millimeters. There's the size. We have the column that comes down. We had to frame around that steel column so the steel column can come down and sit on concrete, because if it's carrying brick, it has to be supported on a solid surface like concrete. So it can't just sit on wood if it's supporting brick. So then we have coming up through the floor, we got this little nib of a wall here. And if we go back here, that's this 810 millimeter high half wall here. And that's coming out from the wall. This is giving a little bit of space probably for a love seat or something to fit in there. And then that's coming straight up, and that's where it comes over here. So that column coming straight up, that's it at the top. This is looking at it from another angle. And you can see that 280 millimeter plate. You see how the mud stops here and the I-beam is up there? That's welded on this corner and on the inside corner there all the way along. And then that has the brickwork that's going up over top the second story, because the second story goes straight through, and this room sticks out only on the first floor. And so that leaves the ceiling inside to be open and flush when it's finished. So it's good to sort of look at these things and envision these kind of things. And that's difficult for you right now, but over time it will get easier. So we covered a lot of different topics in the wall framing. There's a lot of back framing is when you go back and you frame something up. I probably didn't use that term, but the bulkheads around the kitchen, that would be back framing. Framing in for a bathtub in a bathroom, that would be back framing. After the HVAC sub, maybe they got some duct work, maybe we got to put some more bulkheads, that would be back framing. So it's going back and doing that. Blocking is just like you're bridging and filling in between the studs to stabilize the wall. Jack studs and lintels, we looked at all of those, pretty good. Racking with bracing. This should have been on two separate lines. For some reason it's on one. Racking, and then rough opening is a different one. We looked at that. So hopefully that's given you a good sense of wall framing and the parts. I would suggest going through the textbook very carefully, methodically, to try to get a grasp of it. It's not something you can just get like that. It starts to come together over time. Okay, and so just keep working at that, and hopefully it starts to sink in, and you've got questions, make sure to ask me about it. All right, so this is Tom Stephenson signing off for now, and I hope you have a wonderful day. I know I'm going to. It's Friday night.